Hello, my name is Kayla Richardson, and I'm going to be talking to you guys today about my senior capstone, which was a mock research proposal about understanding the conformational state changes of the human mu-Opioid receptor caused by the psychoactive components of Kratom through molecular dynamic simulations. On the agenda today, we'll go through a little bit of background information about Kratom, molecular dynamics, and our overview of our simulation methodology. I'll go through the goals of the experiment and how we'll achieve those, and then we'll talk about why it matters. Starting off with a little bit of background, Kratom comes from a tree that's grown in Asia, and the leaf clippings are often prepared into teas or ground up into powder, which the user can then use however they choose. Kratom has been used for decades, even centuries, as a natural pain reliever. But yeah, within the leaf itself, there have been 30 bioactive indole alkaloids identified and isolated, but I chose mitragynine and 7-hydroxymitragynine because they're both, mitragynine is heavily prevalent in within the plant itself. They have both been found to be highly psychoactive, and they're about 40 times more potent than morphine is specifically on the mu-Opioid receptor. So a little bit about the mu-Opioid receptor, which is what this little tubey thing represents right here. That is a GPCR, which means that it's 7 alpha helices going through the membrane. When activated, these receptors cause activation of different signaling pathways to where transcription factors can be turned on and off. In relation to this experiment, mitragynine and 7-hydroxymitragynine will bind extracellularly to the mu-Opioid receptor, cause a conformational change to where the G protein is recruited, and then we see analgesic effects and usually nothing else other than that. Whereas when something like morphine comes and binds to the mu-Opioid receptor, we see a conformational change in the receptor. Beta-arrestin is recruited or the G protein is recruited. But when the beta-arrestin is recruited, we see analgesic effects. If it's at a high enough biological response, we'll see respiratory depression, and often desensitization happens because the receptor is internalized into the cell. So knowing this, this step right here is honestly really important, where a conformational change happens, which leads me to our hypothesis, which is that variations in the positional changes of the rigid alpha helices of the human mu-Opioid receptor leads to a biased signaling pathway. Thus, the binding event of mitragynine and 7-hydroxymitragynine will transmit the extracellular positional changes of the receptor intracellularly, and these positional differences will be significantly different from those caused by the binding event of typical opioids. Moving on to molecular dynamics. Molecular dynamics is a computational tool that we use to visualize molecules and using Newtonian physics. Quick overview of what we will be doing for this experiment is we would be finding the relaxed state of the receptor, looking at binding studies, looking at the positional changes of transmembrane alpha helices, and looking and investigating the exposure of intracellular residues. So with the first goal, finding the relaxed state of the receptor, we would achieve that through temperature cycling. In this case, this is the overview of what temperature cycling would look like, where we have virtual time on our x-axis and temperature on our y-axis. I will note to you that temperature does not mean the temperature like within the computer or within the simulation. It simply means that we tell the software what temperature we would like it at, and it adjusts the kinetic energy of the atoms within the simulation to that temperature. Knowing that, we would start with our X-chromocosopy structure, heat that up, let it anneal for a second, let it cool down, let it equilibrate into a certain conformation, and then measure the potential energy of that conformation. over here on this first phase, we see that we're actually conditioning the simulation and finding low energy states or low potential energy states that would make us more inclined to believe that that could be a native conformation in vivo. Whereas on the second stage here, we would be understanding those low potential energy states and repeating those temperature cycles as much as necessary. Where here we're more thinking about the actual positional changes of the receptor, where here we're thinking about the potential energy differences of the different conformations. So something that we've learned from this is what an idea of what a graph might look like with the cycle number and the conformation as a bar, and the potential energy as the height of the bar. Ideally, we'd start at a high potential energy state and it would move to a lower state where we would investigate these conformational states that are in these low potential energy wells. Ooh. Jumping all over the place. So this method would be repeated, but not exactly repeated. We'd start off with our crystal structure and we'd insert it into a solvent field where we would find a minimal potential energy state. From that result, we would take that conformation, place it into a water-based solution, and then make that into a low energy state, and then take that result into our plasma membrane. So, identification of binding orientations would be achieved through allowing the opioid and the alkaloids from Kratom to bind in various orientations. Then we would quantify that and we would look at the potential energy change over time for the various binding poses. Looking at those different poses, we would see which one has the lowest potential energy, or which series of poses has the lowest potential energy, and investigate those. Looking more broadly at the entire receptor itself, we would be looking at the conformational state changes of the intracellular portion of the protein. This figure down here demonstrates from a previous paper how the transmembrane helices move. This one is specifically looking at the conservation of movement of the 6th transmembrane alpha helices. So from previous studies, we already have sort of an idea of where to look. Okay, and thinking about the exposure of intracellular residues, this piece is particularly important for thinking about which residues may be more exposed to be chemically modified. So we would look at the root mean squared distance from the oxygen on water molecules in the solvent to the intracellular residues on the intracellular loops of the receptor, knowing that that's where those coupled proteins tend to bind with the receptor. Obviously, these water molecules are super huge, just to kind of give you guys some idea of what we'd be looking at. Remembering again that we're looking at mitragynine and 7-hydroxymitragynine and how those specific binding events might cause conformational changes within that membrane receptor. So, thinking about why this matters, thousands of people die every year from recreational use of opioids, whether that's being addicted from having prescription opioids prescribed to you and then switching over to recreational ones. Whatever the case may be, a lot of people die from them every year. So reducing the amount of people using opioids that have a greater risk of fatality would be very beneficial. And moreover from that, we need to understand a structural basis of GPCR activation better, and I believe that computational simulations could better inform that. Okay, these are my references. And continue. Thank you. Do you have any questions?